So this video gives a brief introduction to disease progression modeling and talks through an implementation of the event-based model in MATLAB. Around 2010, various models like these started to appear, showing hypothetically the sequence of events that occur in neurodegenerative conditions like Alzheimer's disease. These were largely informed by the emergence of multi-center patient data sets showing that early imbalances in proteins in the brain measured from CSF lumbar puncture or from PET imaging lead to the loss of brain cells, which can eventually be seen as atrophy or region shrinkage in structural MRI. That then precipitates reduced performance on cognitive tests and ultimately leads to widespread loss of cognitive function and personality changes. So informative as these models are, they weren't directly informed by measured data, but they inspired various computer science groups to think about algorithms and models that could try to reconstruct pictures like these in a more quantitative way directly from measured data. And that's challenging because the data that we have available to estimate these kinds of model is not uniformly sampled. So it's very difficult to find subjects at these early stages of the disease who are going to progress through the disease journey, because they appear perfectly healthy outwardly, and it's only at later stages that symptoms really start to emerge. Second, even if we can find people at these early stages, it's very difficult to follow them, making dense measurements over the decades that it can take for these diseases to play out. So we don't have the ideal dense longitudinal data sets that we'd like to estimate these progression patterns. But what we do have is short-term cross-sectional or short-term longitudinal data from large numbers of subjects at unknown positions along this disease timeline. And so the modeling and learning challenge in data-driven disease progression modeling is to try to piece together pictures like these from that non-uniformly sampled and short-term data. So I'm going to talk about just one model that tries to do that, to piece together these long-term longitudinal pictures from short-term or cross-sectional data, and it's a model called the event-based model. It's really the simplest model that you can imagine of this type, and simply views the disease as a series of events. And in each of those events, a measurement that we make from subjects or patients transitions from a kind of healthy range to a detectably abnormal range. And what the model then tries to do is to place those different measurements in an order, the order in which they make that transition from healthy value to detectably abnormal value. To give a clearer picture of what that means, here is the kind of output that we get from the event-based model. These are some early results from two different patient cohorts, patients on the path to familial Alzheimer's disease and another group on the path to Huntington's disease. In each case, the set of measurements that we make from the patients comes from structural MRI, and each measurement is the volume of some anatomical region of the brain. So we have a collection in each case of something like 30 different anatomical regions, and a measurement of each of those, the volume of each of those anatomical regions in each of a number of different patients. And the task is to place those anatomical regions in an ordering to show the pattern in which the pathology appears in the brain over time. So these blue bubbles are simply showing the numbers or indices of the different regions from the early stages to the late stages. They've got their names listed from early stages at the top to late stages at the bottom down here. And these red-green brain images kind of summarize that by showing at each particular point the red regions are those which are showing abnormal volume measurements at this stage, whereas the green ones are the ones that are yet to show any abnormal measurements, early stages to the left, late stages to the right. So that's one output that we get from the model, is this, this sort of most likely ordering of measurements. But we also get this picture here, which gives us some insight into where the algorithm is confident in that ordering and where it's not confident. So, for example, in this positional, so we call these diagrams positional variance diagrams. And for example, here, we can see that the algorithm is confident in the ordering of the first three measurements that it looks at. But then there's a block of 5, which it cannot confidently order among the group, but is confident that all of that block of 5 occur after these first 3 and before, say, this block of 10. So that's a nice additional output from the algorithm, is this picture of the confidence in the most likely ordering that it estimates. Here are some later results, now looking at sporadic Alzheimer's disease and showing that the algorithm is not specific to measurements from imaging. This is showing now a model using measurements from various different modalities. There are some measurements that come from measurements of protein levels from lumbar puncture, getting some CSF samples, some measurements from longitudinal imaging, showing rate of change of brain volume, some cognitive test scores, and some cross-sectional imaging volumes as well. So this, again, is showing the positional variance diagram for this most likely ordering on the left here. And here we've computed that uncertainty in the ordering in 2 ways, in a kind of internal way to the algorithm using Markov chain Monte Carlo sampling that we'll have a look at later, versus using a more external evaluation of the uncertainty through the use of bootstrap sampling. And again, we'll look at how to implement this later. And once we've got a model of that type, we can use it to provide a staging system that can help us place individuals on positions along the disease timeline and track their progress over time. So the way that staging system works is simply by counting the number of events in the order that we've estimated that have occurred so far for that particular patient. So someone who's at stage 0, that means that none of the events have occurred. So all of the measurements from the patient or subject appear in the sort of normal or healthy range, whereas someone who's at stage 1 shows abnormality in just the first of that set of measurements that's made from them. And then people at the later stages, if you're at stage 14, showing abnormality in all of the measurements. If you're at the middle stages, say stage 7, then the first 7 measurements in the sequence show abnormality, whereas the remaining ones do not. So that's basically what the model provides. And now we'll sort of dive a little into the technical side of the model and think through how it works and how to implement it. So the first thing that we need in order to implement the event-based model is models of 2 underlying distributions. And those are the distributions on the values of each of the set of measurements that we make, given that the corresponding event has not occurred and has occurred. And if we think of those in turn, so first of all, the distribution of measurement values given that the event has not occurred, this is just the distribution of measurement values in the normal healthy range before the measurement has transitioned into providing a detectably abnormal value. So in situations where we have a well-defined control group of subjects, in addition to a set of patients, and this is very often the case in research studies, it's very straightforward to fit a model for this distribution of measurement values given that the event has not occurred, because we can just fit it directly to the set of measurements that we get from our controls, who by definition have not undergone this event to show abnormality in any particular measurement. So that directly gives us an estimate for the for this distribution of measurements given event has not occurred, we have to work a little harder to estimate the distribution of measurement values given that the event has occurred. Although we have the distribution of measurements from our set of patients, it's not that each patient hasn't necessarily undergone the event that turns the measurement, that particular measurement, to an abnormal measurement. Because some of those patients will be at early stages before that event has occurred, whereas other patients will be at later stages, so that event has occurred. However, we can view the distribution of measurements from patients as a mixture of samples from the distribution of measurement values given that the event has not occurred, those would come from patients at the relatively early stages, and samples of the distribution of measurement values given that the event has occurred. Those would be the patients at the relatively later stages. And so we can then obtain a model for this distribution P of X given E by fitting this mixture distribution to the distribution of measurement values from our set of patients. And that's particularly straightforward in the case where we've got a control distribution, because we already know what this distribution looks like. So we only then have to estimate the parameters of the P of X given E distribution and this mixing parameter F. There are various distributions that people use for the various parametric models that people use for these two distributions. Very often we will use simple Gaussian distributions to model P of X given not E and P of X given E. And in that case, then this is all quite straightforward. We just have to estimate the mean and standard deviation of these two distributions. Once we have models for those two distributions, we can then start to construct a likelihood of our full set of data given any particular sequence. And once we've got the likelihood of our data given a sequence of events, we will then search for the sequence of events that maximizes the likelihood of that data. So the first step in constructing that likelihood is that we construct the likelihood of just one patient's set of data. So big XJ here is the set of measurements from one particular patient, patient J or subject J. And we'll start by evaluating the likelihood of that data on the assumption that we know what the sequence is and at what stage that particular subject is at when the measurements were made. So on that assumption then, we can write the likelihood of this patient's data given the sequence and the stage as in terms of the likelihoods of each individual measurement given that the event has or has not occurred. And if we assume then that this subject is at stage Kj, we get the likelihoods of the first Kj measurements from the likelihoods of the measurements given that the event has occurred. That's the definition of being at stage Kj, the first Kj events have occurred. We'll assume that each of the measurements is independent, so we simply multiply together the likelihoods of each of those first Kj measurements given that the corresponding events have occurred. And then for the remaining n minus Kj minus 1 measurements, the assumption as they're at Kj is that those events have not occurred. So we multiply then the likelihoods of the remaining measurements given that the corresponding events have not occurred. And this big product then gives us this likelihood of the full set of data from one particular subject given the sequence and the stage. Of course, we don't really know what stage any individual is at. However, we can then obtain a likelihood of the patient's data given the sequence by simply integrating out this hidden stage variable Kj. We do that just by summing this likelihood that we computed on the previous slide over all possible stages, weighted by some prior on the individual stages. Generally, we'll assume that that prior is uniform, so because we have no a priori information about any particular stage being more likely than any other. So that gives us these likelihoods of each patient's set of data given the sequence, and then to get an overall likelihood of our full set of data X given the sequence, we simply multiply all of these likelihoods of the individual patient's data together on the assumption that the measurements made from one patient are independent of measurements made from any other patient. So that's our overall likelihood of the data given the sequence. We can substitute these various expressions back in to expand it in full. This is just substituting the expression from the previous slide into here. So we can evaluate this then for any sequence S, and we'll then, what the event-based model does is to seek the sequence S that maximizes this likelihood. So in the fitting stage of the model then, as I just said, we seek the sequence that maximizes this likelihood. And there are several ways that we can go about doing that. The simplest way, if the number of events or number of measurements is sufficiently small, so n is small, is just to evaluate this likelihood for all of the n factorial possible permutations of the ordering. And that's tractable up to n is, I don't know, something like 10 or 11, but much higher than that, then it starts to become too computationally demanding to do exhaustively. So we need alternative strategies to find that most likely sequence. And the standard approach to doing that is to use a fairly simple greedy search to identify the maximum likelihood sequence. And we'll see an implementation of that in a second. So that greedy search will then find the single most likely sequence. But of course, there's an additional output to the model, which was these positional variance diagrams I talked about earlier. And the way that we do that is through a sampling procedure. The main approach to doing that is using a Markov chain Monte Carlo sampling algorithm to build up a picture of the more complete posterior distribution of the sequence given the data. And again, we'll see an implementation of that shortly. So I'm going to switch modes now to implementing this idea in MATLAB. I have taken the liberty of preloading a data set to test the event-based model on. This is a data set representative of a familial Alzheimer's disease cohort. And if we take a look at what's in the data set, so we have an array data which contains 10 different measurements. They are all, as we saw earlier, volumes of different brain regions, contains 10 measurements of anatomical brain region volumes from each of 500 different subjects. And some of those subjects are control subjects, some of those are patients who are either at showing symptoms of the disease or at pre-symptomatic phases. The array DX actually tells us which of those subjects is a control subject and which is a patient. We won't actually need to use that here. This array EBM labels, we'll have a look at it, gives us the names of the different brain volumes. So don't worry too much about these if you're not familiar with brain anatomy, but just for completeness. So the names of the different brain volumes are the frontal lobes, the corpus callosum, the right and left motor strip, orbitofrontal gyrus, amygdala, entorhinal cortex, hippocampus, temporal lobe, and brainstem. As I say, don't worry too much about those, but one thing that might be worth bearing in mind is that the entorhinal cortex and the hippocampus are both memory-related areas that we would expect to show early disruption in Alzheimer's disease. So we might expect to see these two areas, in fact, the temporal lobes too, in these three areas somewhere near the beginning of our sequence of events. Let's take a quick look at the data array then. I won't print out the whole thing, but let's maybe look at the first few rows just to understand its content a bit. So I'll print out the first 5 rows of that. So the top row here then is the set of measurements of these different volumes of these different brain regions for patient number 1. second for patient number 2, and so on. I'm just going to draw on this virtual whiteboard the various objects that we are using here. So we'll start with our data array. So this then is a 2-dimensional array. Like so. And it has size. So we will call the number of measurements n, that's 10 here, and the number of subjects j. And just to make the link with the notation I used on the slide, so any particular element of this data array then is measurement x, I, j. It is the ith measurement from patient j, and a particular row of this matrix is then the set of measurements, set of all 10 measurements from a particular patient. We call that capital Xj, and the full set of data then is just capital X. So I'm going to start by extracting those. I'm just going to define those numbers j and n because we'll use them during this implementation. Get it directly from the size of that array. Now, you'll recall that the first thing that we need to do is to compute these measurement distributions P of X given E and P of X given not E. So here I've pre-computed those distributions because the implementation of the estimation of those distributions gets a little bit fiddly. If you are interested in how that's done, let me just go back to the corresponding slide. Oops, this one here. So you can find code that implements the estimation of the parameters of these two distributions on this GitHub here, which implements the event-based model. However, here they are contained in the last of the preloaded arrays here, p hat. If I just print out p hat, I'll explain what it contains. So p hat has 10 different rows, one for each of our 10 different brain volume measurements, and we're using Gaussian distributions for each of the Gaussian models for each of these two distributions. The first two columns here are the mean and standard deviation of P of X given not E, and the third and fourth rows columns are the mean and standard deviation of P of X given that the event has happened. This last column here is that mixing parameter F. We won't actually use that here, but it's included in the array just for completeness. Okay, so the first thing we're going to do is to compute two arrays of the same size as our data array. I'm just going to draw it down here. That will contain the likelihoods P of X given E and P of X given not E for each of the measurements in our data set. So I'm going to construct two arrays of the same size. The first one I'm going to call L no, and the second one I'm going to call L yes. So this again has size n columns and j rows. And L no will contain P of X given not E, and L yes contains P of X given E, i.e. event yes, event has happened, and no, event has not happened. So then the individual elements then of this array contain precisely that. So for P, L, no, that element, any particular element here would contain the likelihood of P of X, I, J, given that event I has not happened. So this is the ith measurement from the jth subject, its likelihood given that the ith event has not occurred. So assuming that it's coming from the normal range. And then for LES, equivalently, this array will contain P of X, I, J, given that the ith event has occurred. Okay, so that we're going to compute these two arrays, LES and LNO. And that's very straightforward to do simply by computing the likelihood using the normal distribution function defined by the parameters in this P hat array. So let's go ahead and construct these arrays then. I'll start by just creating some empty arrays in which to store these values. So LNO as, I'm just going to start with an empty array of zeros, the same size as our data array. Same for LES. And now we're just going to loop over each column of LNO and LES and evaluate the likelihood of each of those, each of the data points according to the models for P of X given event has occurred and P of X has not occurred. So looping then over each of the n columns. We can write L no of the first column as norm PDF. So that's evaluating the probability density function of the normal distribution for the first, or the kth column of our data array. Those are all the kth measurements for the individual patients. With mean P hat K1 and standard deviation P hat K2. And similarly, LES, I'm just going to cut and paste this line because it's exactly the same, only that the parameters of the normal models for the distributions given the event has happened come from now P hat rows 3 and 4. So that's evaluated those. Let's just have a quick look at some of the contents of these arrays just to sanity check and get an idea of what's there. So let's look at the first, I don't know, 5, just maybe first 3 rows of LNO. So these are the likelihoods of the measurements. The top row here is the likelihood of each of the 10 volumetric measurements, given that those 10 events have not occurred, and they're all sort of, probabilities between 0 or density function values, sensible values for a Gaussian distribution with a mean of approximately 1, and LES should have kind of similar range of values in it. There we go. Okay, so the next object we're going to construct will evaluate, if I just flip back to the PowerPoint slide for a second, we'll evaluate these probabilities, the probabilities of each subject's full set of measurements given a particular sequence, and for each of the possible stages that subject might be at. So we're going to evaluate these products for each of the different stages given a particular sequence and for each of our different subjects. So I'm going to construct a new array now. I'll draw it again on our whiteboard. I'm going to give it a slightly cumbersome name of subject likelihood given sequence and stage. Slightly cumbersome variable name, but at least it tells us what it means. So this is going to have now similar size to our data and LES and LNO arrays, but it's got one extra column in it because there's one more stage than there is number of different measurements, because we can have stage 0 when none of the events have occurred, all the way up to stage n where all of the events have occurred. So this then has size n plus 1 columns, and is, as usual, defined for each of our subjects. And the contents of this array is the likelihood of x j given a particular sequence and stage j. Any particular element contains that. So we're going to evaluate this array for a particular sequence to start with, and we're just going to pick a sequence at random. So I'm going to obtain that using MATLAB's rand perm sequence. So rand perm n produces a random permutation of the integers 1 up to n. So there it is. The integers 1 up to 10 in a random order, and we'll use that as our starting point for the search of the most likely sequence. So given that, then we can construct our array subject likelihood given sequence and stage. I'll just set it as an empty array to start with. So of course it has size j n plus 1. And then we'll construct it column by column. So for k equals 0 up to n, then subject likelihood given sequence and stage column k plus 1 is equal to the product of the first of L yes for the measurements that are before the stage that we're at, so before k. So we product together L yes for measurements 1 up to k in our ordering. So if we were at stage 2, say, we would want to multiply together L yes for measurements 6 and 7 here. So first k of our measurements give us an L yes. And we want the product to be over the second dimension of that array, which is the rows rather than the columns. You have to specify that here. And then multiplied by the remaining measurements evaluated using LNO, because if we're at stage k, then the assumption is that the events have not occurred for those later stages beyond later measurements at later points in the sequence. So that would be k plus 1 up to the last of those. And again, we're going to do that over the second dimension of the array. Okay, so that's that array constructed. Let's just have a look at some elements of that array. So maybe if we print out the first kind of 10 rows of that, and give you some insight into what that array contains. So print out the first 10 rows. So what you can see here is that these are then likelihoods of these individual subjects' full data set given this particular sequence for each particular stage. So this one here is the likelihood of subject one's full set of measurements given this sequence up here, and that subject one is at stage 0. And you can see how that evolves as we go across the stages. So actually for this particular subject, the highest likelihood for them is this one here. So that given this sequence, their most likely stage is this stage 4 here. Whereas for subject number 2, their most likely stage given this sequence is the very last one. They're most likely to be at the end. And actually subject number 3 is most likely to be at the beginning. And you can see that the different subjects, this likelihood peaks at different stages depending on where they are through the journey of the disease. Okay, now that we've got this, the next thing that we're going to do is to then sum. You recall, if we go back to the PowerPoint just for a second, the next stage was to integrate out this hidden variable k by summing over all possible stages. So we are going back to the virtual whiteboard here, if we sum along the rows of this big matrix that we just constructed, we'll get a single column matrix containing P of xj given S, having integrated out the hidden variable k. Let's go back to MATLAB and we'll do that. So first of all, we need to define that prior. So let's say the prior on k, we'll assume a uniform prior. So we'll just define it as 1 over the possible number of stages, which is n plus 1. And then we can compute the subject, I'll call it subject likelihood, given now just sequence. And we do that by summing prior on k times this big array that we just constructed up here. And we'll sum it again along the rows, so we need to define that dimension. And that will give us this big, this column array that we just wrote down on the virtual whiteboard here. Let's have a look at it. The first few entries at least. And that kind of makes sense if you think about it, because we're summing over these things, so the values are sort of pretty much the highest values that we see in these different rows. So I think we're on track with that so far. And then finally, the next stage to construct our likelihood of the full data set given this particular sequence that we chose is simply to take the product over all of the different subjects. So on our virtual whiteboard again, that's just taking the product down this big row that we've just computed to obtain probability of full data set given this particular sequence that we chose. So back to MATLAB to do just that. One thing we have to be a little wary of here is that if we multiply together 500 values, all of magnitude 10 to the minus 7 to 10 to the minus 10, we'll have an underflow problem. We won't be able to store that number. But what we're going to do instead is compute the log likelihood to avoid that. because as we know, the log of the likelihood will have the maximum point for the same sequence as the likelihood itself, because it's a monotonic function. So we can compute then the sequence log likelihood is the sum of the log of this array that we've just computed, subject likelihood given sequence. And let's print that value out just to see what it is. So we end up with this value of minus 8,000. Okay, so that's the evaluation of the likelihood. Now let's turn our attention to how, now that we know how to compute that likelihood, how can we search for the sequence that maximizes that? And if you recall from the slides, I said, so we could do this through exhaustive search of looking at all the possible permutations, but actually we're going to use instead a greedy search strategy, which scales up to larger numbers of measurements. So we'll start by doing that. And this search strategy is going to be very simple. All we're going to do is to start with a random sequence. We've already chosen a random sequence, and we'll just use that as our starting point. And we're simply going to pick two elements of that sequence, swap them, evaluate the likelihood of the new sequence with those elements swapped. And if it's bigger, we will choose that new sequence instead, and then repeat the process. If it's not bigger, we just stick with the old one and repeat that process lots and lots of times until we end up with a sequence where we can't find a swap that increases the likelihood. And we'll call that our maximum. So a very simple optimization strategy. Let me just implement one iteration of this first, just to illustrate. So first of all, I'm going to choose two different indices, or two indices. I won't necessarily come out different, actually. I'm going to choose two indices of our sequence, and I'm going to do that here. So this is a random number between 1 and n, just to unpick that slightly. So what I've done here, rand is a MATLAB function that gives me a random number between 0 and 1. Multiply that by n, it gives me a random number between 0 and n. Then I'm taking the ceiling of that real number, which will give me an integer in the range 1 up to n. So that will give me a random index into my sequence. Okay, so that will be move index number 1. I'll do the same for the second index that I want to swap. Let's have a look at them. So, okay, we've chosen 3 and 4. So let's then, let's create a new version of our sequence that swaps those two around. Just cut and paste that. Let's just check that's done what we expect. So here is our old sequence, and here is our new sequence. Should have permuted elements 4 and 5. Indeed, it has. And then, so let's then recompute the likelihood of sample sequence now that we've swapped those two around. And if I just go back up to my earlier code, I can just repeat several lines of that from here. So I just need to recompute my subject likelihood given sequence, and then the subject, oops, what's going on there? Recompute again. So I need to recompute from there down to the sequence log likelihood. So let's just do that. down to there. And so we get a new likelihood of minus 8.8, so minus 8,853, whereas previously, if I scroll back up, we had minus 8,778. So actually our previous, the previous sequence had a higher likelihood. It was less negative than this new one. So in this particular case, we would have kept the old one. Okay, so let's adopt that strategy then, and we'll put it into a greedy search loop here. I'm just going to run it for a slightly arbitrary, but I happen to know it's enough, 1,000 iterations. And I'm going to store my set of samples as this greedy search iterates. I'm going to store the sample at every iteration. So the sample being the sequence that we retain at each iteration of the greedy search. So that will be an array containing length of a sequence at every one of those iterations. And I will also store the likelihood, or the log likelihood of each of those sequences during that search. So that will just be a single number at each iteration. So I'll start with our the current sequence. What do we call it? Sample sequence. Samples 1. And the sample, the first sample log likelihood then will be the likelihood that we just computed. Sequence log likelihood. So now for I is, well, we've done one iteration already, haven't we? So we're going to start with iteration 2. I'm going to start by doing my computing those move indices again. And then I'll copy the previous iteration into sample sequence. So starting with where we were at the previous time around the loop, then performing the swap. And the other one, cut and paste that this time. Okay, and then having done that, we can simply compute the likelihood using the exact same code that we used before. So I'm just going to paste that in, cut and paste it again. There it is. So the same, computing this big array here, and then summing across the rows and taking the product down the column. That gives us the sample, the new sample likelihood. And so now we've just got to make the decision about whether we want to keep this new sequence or stay where we were with the old one. So we simply compare the new sequence log likelihood with the likelihood from the previous iteration. So that will be sample log lix I minus 1. So if the likelihood of the new one is bigger, then we're going to set the ith array, the ith element samples to be the new sample sequence. And similarly, the ith element of sample log lix to be this new sequence log likelihood. Otherwise, we keep the, we just make a copy of the previous element of the samples array. And okay, so that's executed those 1,000 iterations pretty quickly. Let's see what's happened. So if we start by looking at, let's look at the evolution of our log likelihood over these 1,000 iterations. I'm just going to plot that set of log likelihoods. So there they are, and what we see is that we start, as we saw, we started at something like minus 8,800, and gradually by doing these swappings and taking the greedy approach of taking anything that has a higher likelihood, we seem to end up with a a stable choice towards the end. There's obviously no guarantee that we found the global minimum here with this simple greedy search strategy. It can, of course, fall into local minima. However, I've run this program many times, and every single time it has always converged to the same sequence. So I'm confident here that we have found the global maximum. I've also done the exhaustive search to prove it. So although it's not guaranteed in practice, it does seem that this greedy search for this particular problem is very good at finding the global maximum solution. I could run through this again from a different starting point to check it, but in the interest of time, I won't do that. You can try it yourself if you want to verify. But interestingly enough, every time we run this greedy search, it will converge to the same sequence that has this likelihood here of something like minus 7,900, whatever it is. Let's have a look at that sequence. So we'll copy it out into a new variable called best sequence. So it's the last row of the samples array. There it is. Let's index our EBM labels. Remember, this was the array of names of the different brain regions. So let's index that with the elements of our best sequence, and that should give us the list of brain regions in the order that they show abnormality. And this looks sensible because if you'll remember, I highlighted two particular regions, the hippocampus and the entorhinal cortex, as being memory-related regions, which are likely to be the ones that are affected most early in Alzheimer's disease. And then we get these various other ones following that order. So that seems like a reasonable outcome. I'm just going to copy the samples array into two different arrays, greedy samples, just to have them, because I might reuse them later. And I'm going to reuse this array called samples for something else in a minute. Okay, so that was the greedy search for finding the maximum likelihood sequence. The next thing, if you remember, going back to the slides, so that the maximum likelihood sequence was one output from this procedure, but we also estimated this positional variance diagram that gave us an idea of the confidence in the different components of that sequence. And we're going to move on now to look at a different stage of the processing, a different stage of processing, which will evaluate that uncertainty picture. And going back to my last slide here, the way we're going to do that is to use a sampling algorithm called Markov chain Monte Carlo to construct a set of samples of the posterior distribution on the sequence given our data set. So here's some pseudocode on this slide that outlines how the MCMC sampling algorithm works. And actually, if we look at it, you'll appreciate quite quickly that it's very similar in structure to the greedy search that we just implemented. So let's just pick through this. So first of all, we start with some sequence. We're actually going to start with the best sequence that we found from our greedy search process. Then we're going to swap two randomly chosen events within the sequence to create a new sequence S star. That's exactly the same permutation that we used in the greedy search. Then something is slightly different. So the only thing that's going to change between our greedy search and the MCMC is the way that we decide whether to keep the new sequence S star or stick with the old one ST. So this time what we're going to do, this is the classic step in MCMC, is to evaluate a likelihood ratio, which we'll call A, which is the ratio of the likelihood of the data given our new sequence to the likelihood of the data given our old sequence. And then we accept the new sequence with probability, the smaller number out of this likelihood ratio and 1. What that means is if our new sequence has higher likelihood than the old one, so that means A is greater than 1, the minimum of these two is just 1, so the probability, with probability 1, we accept the new sequence. In other words, if the new sequence has higher likelihood, we accept it. Exactly as we did with the greedy search. The only difference is that with MCMC, we may accept the new sequence even if it has a lower likelihood than the previous one. So if the likelihood of S star is lower than the old sequence S star, let's say it's half of it, so that our likelihood ratio is 0.5, then still with probability 0.5, we'll accept the new sequence anyway, even though it's got lower likelihood. So this is the classic MCMC algorithm. It always works this way. It's beautifully simple, but very nice because provably converges on a set of samples that approximates the posterior distribution on the parameters, which means that each sequence will appear in that list in the final list of samples that we get from MCMC. Each sequence will appear a number of times that's proportional to its likelihood, its likelihood relative to the most likely sequence. So let's jump back to MATLAB and we will implement this sampling algorithm. So we're going to use the exact same code structure that we used for the greedy search a minute ago. The MCMC requires kind of larger number of iterations. So the only thing I'm going to do is define a larger number of iterations. Let's do 100,000 this time rather than 1,000. And so I need to then redefine my samples array, zeros, number of iterations. Okay. And similarly, sample log likelihoods now needs to be bigger than it was before. Number of iterations. Okay. I'm going to initialize the first sample, our starting point for this MCMC procedure, to be the last element of our greedy search. So the last sequence we found was greedy samples end colon. And similarly, the first element of our new sample log likelihoods will be the last element of our greedy sample log likelihoods. Okay, so now we're in a position to start it. And as I say, that the code structure is basically the same as the greedy search that we just did, to the extent where I can pretty much cut and paste all of the first few steps. So, in much the same way, we create a permuted sequence where we just swap two elements and create and calculate the likelihood of that new sequence. That's exactly the same. So I'm just going to cut and paste it down there. The only thing that changes, of course, going back up to our greedy search here, is this condition on whether we accept the new sequence or retain the old one. Now, of course, we have to compute this likelihood ratio. So I'm going to do that here. So the likelihood ratio then, of course, is the fraction, the likelihood of the new sequence divided by the likelihood of the old sequence. Of course, here we're working with log likelihoods. So that fraction will then be the exponent of the difference of the logs. So I'm going to write this likelihood ratio as exponent of the likelihood of the new sequence minus the likelihood of the old sequence. That would be sample log x I minus 1. That would be our likelihood ratio. And then, so the condition on accepting the new sequence will be simply if that likelihood ratio likelihood ratio is greater than a random number between 0 and 1. Because if the likelihood ratio is greater than 1, it will always be greater than rand. Rand produces a uniformly distributed number between 0 and 1. And if likelihood ratio is less than 1, then this is precisely the condition that I outlined on the slide. Okay, so if that is the case, then we accept the new sequence, and if not, we accept the old. So again, I can just cut and paste my code from up here that did that in the greedy search. Okay, let's let that run. That will take a little while because it's doing 100,000 iterations of this MCMC, so it will produce a long list of samples, 100,000 samples. We'll have a look once it's computed it. Once it has done it, I'm going to use a MATLAB function called unique, which will pick out all of the unique rows of that set of samples. Okay, it's run. So unique, you can set it to rows, which means it will identify all of the unique rows of our list of samples that's come out of this MCMC procedure. I don't want to look at them all because it's a massive array. So S should contain, okay, so it's only identified 4 unique sequences in that huge long list of 100,000 different sequences. It appears that there are only 4 that have got a likelihood that's high enough ever to be able to pass this likelihood ratio test. And if we look a little bit more closely, we'll see that really there are only 2 pairs of indices, not the 9 and the 10 here in positions 3 and 4, and the 3 and the 4 in positions, whatever these are, 8 and 9, that can viably swap to produce a likelihood which is close enough to the maximum likelihood sequence ever to appear in this in this list of samples that the MCMC generates. Let's just have a look at the relative likelihoods of these different sequences. So I can actually index our sample log likelihoods array using the, so A here is the indices of these unique sequences in the big samples array. So we can look at the equivalent indices of sample log likelihoods to see the likelihood of these different sequences. And what we see then is that our maximum likelihood sequence, the best sequence that we had from before, is this third one here. That's the one we looked at previously. And the second most likely is what is this one here, isn't it? So it's easier to swap 3 and 4 by the looks of it than it is to swap 9 and 10. Actually, also informative just to look at the evolution of the likelihood over this sampling procedure. So here it is. So what we see is that, you know, this sampling procedure just basically sort of jumps between 4 different points. So that it will visit the most likely sequence, the one with the highest likelihood here, the most number of times. Reasonably regularly, it will jump down to the second most likely sequence. A bit less regularly, it will jump down to the third most likely, and very occasionally this fourth most likely. And the number of times that it visits each of these different sequences, it reflects the relative likelihood of each of these sequences being the right one. So I said, you know, I mentioned that the point of doing this, of course, was to generate figures like those positional variance diagrams. Let me just go back to that again, just to remind you what it looks like. So these pictures here. And you'll recall that what these pictures show is, so that the way that we construct these pictures from those lists of MCMC samples is each element of this is the number of times that this marker with this position in the maximum likelihood sequence, which is on the y-axis here, it's the number of times it appears in each of these positions in the sequence over that whole list of MCMC samples. So if we look at A beta, for example, in every single one of the MCMC samples, it appears in position 1. It's very confident that it lives there. But if we look at P tau, it comes second in the maximum likelihood sequence, but actually over our list of samples, it usually appears second, but occasionally appears third. And similarly, T tau, third in the maximum likelihood sequence, and it's usually there, but occasionally it appears second. And so to construct this picture, all we need to do is count over the set of MCMC samples, how often each of these positions appears in each position in the sequence. So pretty straightforward to construct. The size of the positional variance diagram must be simply n by n. So let's fill it with zeros to start with, and then I will just loop over each element of that array. And what goes into element ij is simply the number of times that the MCMC sample for that particular position equals the corresponding element of the most likely sequence, which I think I named best sequence sometime earlier tonight. So we just compare the number of times, we compare whether or not they're equal, and add up the number of times this comparison evaluates to 1. And then rather than creating a figure, I'll just print it out. So this is what it looks like. So Again, we see that the third and fourth elements and the ninth and eighth and ninth are the only ones that commute occasionally. Most of the time, they're in the maximum likelihood configuration, but occasionally they flip to the other one. So you can imagine what that would look like as a positional variance diagram figure. Okay, so that's the MCMC procedure, creating that positional variance diagram. We're just going to do one last thing before finishing this video, which, if we go back to our slides again briefly, is to compute the positional variance diagram in a slightly different way. I described it as an external way earlier. Actually, the way we're going to do that, alternative way of estimating it, is to use a bootstrap procedure. This MCMC procedure tends to underestimate the uncertainty, whereas the bootstrap gives a slightly more realistic estimate. I'll just go through the implementation of it first of all, and then I'll talk about the pros and cons of each approach a little bit at the end. So the way the bootstrap works is to resample the data at every iteration, and then go through the whole process of fitting the event-based model again. And so it generates samples from a perturbed data set each time around the loop. The way it generates that perturbed data set, so we start with our data array again. Yeah, let me just draw it again. This is our data array. So if this is our original data array, the way we construct a bootstrap data array is by sampling rows of our original data set and copying them into our bootstrap data set with replacement. So for example, this is x1, the first row of data, x2, all the way down to xj. For the first row of our bootstrap data set here, we randomly select one of these rows and put it as the first row of our bootstrap data. So let's say we randomly happen to choose x200, or somewhere in the middle, x250. We put that as the first row of our bootstrap data set. Choose another random row, happens to be x461. Put that as the second row. Randomly choose another, happens to be x6, and another happens to be x250 again. So we can repeat the same row every time we choose a random one, doesn't matter if we've chosen it before, and so on, and just keep going until we get all the way to the end. So some of these rows will be repeats. Some of the rows in the original data set won't appear in the bootstrap data. That doesn't matter. We just simply construct the bootstrap data set that way, and then repeat the whole fitting process that we did before to identify the maximum likelihood sequence. So let's go through that quickly. It's pretty straightforward because we've already done the fitting once we've constructed the data set. I'm just going to cut and paste our greedy fitting procedure. The only thing that we haven't done is the construction of the bootstrap data set. So let me start by doing that. We're going to do it again every time round a loop. So we build up a set of samples, much as we did with the MCMC procedure. But this time we're going to perturb our data set each time around the loop. So I'm going to start by making a copy of my data set just so I don't lose it. Let's copy it into the original data there. Then I'll define a number of iterations of the bootstrap. I'm going to make it a bit smaller this time because this takes a little while for each iteration. So I'll just do 100. In reality, we'd do a lot more, but just to keep the video reasonably short. So we'll do 100 iterations, and I'll create an empty array of bootstrap samples. Like so. And then Let's initiate a loop then. So for every one of these iterations, I'll call them B. So I'm going to just, so that I know it's working for sure, when I actually come to run it, I'm just going to display something at each iteration. So we'll just display the iteration number each time around the loop. And now let's create this, this bootstrap data set. So the way I'm going to do it is to construct an array of random indices in the range 0 up to j. And do that in much the same way that I created the random indices into our sequence earlier. So the ceiling of rand j comma 1. So rand j comma 1 is going to give me an array of size of length j of random numbers between 0 and 1. Multiply them by j itself and give me an array of random numbers between 0 and j. And then when I take the ceiling here, that gives me an array of length j of random indices between 1 and j. So the number of indices into the rows of the data matrix here. That's what I'm doing there. Okay. And then from that, it's pretty straightforward to construct my new bootstrap data set by indexing the original data set simply with those bootstrap indices for the rows. Okay. And then having done that, we're now in a position to just rerun our previous code that that did the greedy search. One thing that we have to do every time around the loop, which we didn't do previously, if you remember, we just scroll back up here a bit, is to recompute these no and yes data sets, because arrays, because of course these depend on the actual data set, not just the sequence and so on. So each time around this loop, we've got to go back to recomputing yes and no, and then the subsequent subject likelihood given sequence and stage and so on. We've done all this before, so I'm just going to cut and paste the code from earlier. So first of all, here's the bit of code that computed the yes and no arrays. Paste that into our loop here. Here it is. Then I'm just going to do exactly our greedy search. I'm going to cut and paste it from earlier, starting from computing a new random sequence. So let's do that first of all. Just going to paste exactly what we did earlier. There's a new random sequence, and then construct the arrays that are going to contain our list of samples and so on from our greedy search. There they all are. Number of iterations, we'll do 1,000 each time around this 100 bootstrap loop. So it's going to take a little while to run this, but never mind. And then here is our greedy search loop. Here it is for I equals 2 to number of iterations. We do our greedy search. And then, so the last thing then that we need to do once we've finished that search, I'm going to extract the final sample from our greedy search and put it into element B of our bootstrap samples array. So I'm storing the best sequence from each time we run this greedy search. Okay, so here it goes, running through its 100 iterations. And once we've done that, I'm just going to construct the positional variance diagram in exactly the same way that we did before. So I'm just going to search for that little bit of code while that's running. This was it. This time, so we want, this was the bit of code that computed the individual entries to the positional variance diagram previously. Now, of course, we want to use our bootstrap samples. There they are. And compare those with our best sequence. And let's just have a look at how that's changed. So we see, yeah, so we see quite a lot more, not a lot, but a little bit more variation with the bootstrap sampling compared to the sampling from the MCMC that we saw before. So yeah, those are really the two ways that we typically go about computing the uncertainty and the ordering from the event-based model. Just one thing to say about both of these. In fact, both the strategies I've showed you here will tend to underestimate the uncertainty. And the reason being that neither of them has accounted for some of the parameters that we estimate during the process of fitting the event-based model. Specifically, we've only allowed in the MCMC, we only allowed the sequence itself to vary. But of course, you'll remember that the first thing we estimated was the parameters of these distributions. So strictly, the MCMC should be varying both the sequence and the mean and standard deviations of these two distributions. And similarly, the bootstrap procedure. So actually, in a paper I'm referring to here, this was done properly, but we should really, every time around that bootstrap loop, we should be recomputing not just LNO and LES with the new data set, but the two distribution models, P of X given E and P of X given not E, which I think is what they actually did in this paper, which is why you get a broader, substantially broader uncertainty picture of the uncertainty here than you do from the MCMC, which doesn't vary those distribution parameters. Okay, that's the end of this introduction to the event-based model.